నిజంగా స్టార్ట్ చేయొచ్చు కదా. Okay, good morning student friends, and also once again thank the organizers for spending their valuable time for the noble cause of giving online coaching to the students of Andhra Pradesh. Yeah, we are discussing the chapter of analysis of fluid flow. Earlier we have discussed all the other important chapters. So analysis of fluid flow we are discussing, and will be going for objective questions, interesting questions of gauge, and we have discussed about all these things. Reynolds experiment, and this is experiment we have discussed yesterday, and we have a laminar flow. So if you see here, when the filament it is tight and stable, so if the fluid flows steadily and regularly without any mixing, you can say it is a laminar flow. In between laminar and turbulent is a transition flow where it has shown irregularities, and the transition between laminar and turbulent, this is the case here, and critical velocity in which the flow changes from laminar to turbulent. This is the turbulent flow here, wherein you can see here the irregularities became more intense, and finally there is a diffusion over the entire cross section. Erratic, irregular motion is turbulent flow. And we have a Reynolds number which is Vd, velocity into diameter by kinematic viscosity, and it is defined as inertia force to viscous force. When it is less than 2000, it is laminar flow. When it is more than 4000, it is turbulent flow. And we have a Darcy-Weisbach equation. Sometimes it is also called Darcy's equation, but both equations are same. Both the names are same. So HF is head loss due to friction, which is equal to F into LV square by 2ZD. F is the quotient of friction, L is the length of the pipe, and V is the velocity, and D is the diameter. Hydraulic mean radius, which is R, and R is equal to area by weighted perimeter. So when it is circular, A is square by 4, and P is weighted perimeter. S is the slope here, HF is the head loss due to friction by length L. So change this formula for finding out the velocity V, which is equal to C into square root Rs, and R is hydraulic mean radius, and S is slope here, and Manning's equation also for finding out the velocity, which is equal to 1 by N into R to the power 2 by 3 into S to the power 1 by 2. And this is the uniform flow here, and energy losses in pipes, a very, very important topic and need to remember. We have different losses are here. One loss is, so major losses means when the length of the pipe is more than 1000 times the diameter of the pipe, can take it as a friction loss as a major loss. That is HF is equal to FLV square by 2ZD, and head loss due to sudden enlargement is equal to V1 minus V2 whole square by 2Z. Head loss due to sudden enlargement, velocity before enlargement and velocity after enlargement, V1 and V2. And head loss due to sudden contraction. So this kV square by 2Z, where V is the velocity after contraction. Remember that this V, because we have only single V here, head loss due to sudden contraction is kV square by 2Z, and V is the velocity of the water after contraction. So where K is equal to 1 by Cc minus 1 whole square, and Cc is the quotient of contraction. During absence of data, we can take it is K is equal to 0.5. So the head loss due to sudden contraction is also equal to 0.5 V square by 2Z, provided Cc is not given. Entrance loss is 0.5 V square by 2Z. Again, entrance loss, this velocity, the velocity of water which is entering the pipe is V here, 0.5 V square by 2Z. Exit loss here, exit loss is V square by 2Z. And when the water is exit into another pipe, another tank, then it is velocity of the water which is exit at the location of exit. You need to take V here. It is not the starting point, it's exit here. Again, bend loss not necessary. It has not given any problem on that. But bend loss is you can take kV square by 2Z. When the pipes are bent, it's a minor loss. Sometimes, most of the times, they may ask you to neglect minor losses. In that case, you all neglect minor losses and take only friction loss. And net loss due to sudden gradual contraction enlargement, which is equal to K into V1 minus V2 whole square by 2Z. All these equations are very, very important for the problems which are going to do now. immediately. So this is sudden enlargement when the pipeline is suddenly increase its diameter, and this is sudden contraction when it is suddenly contracted here. And the relation between coefficient of friction and the Reynolds number is also important for lambda number of questions. You can see the questions of gate, and those questions are related to these two equations also. You need to remember that when the flow is laminar, you take F is equal to 64 by Rn. When the coefficient of friction is when it is Reynolds number is less than 4000, when the Reynolds number is less than 4000, you need to take you need to take Fn is equal to 0.316 by Rn to the power of 1 by 4. Rn to the power of 1 by 4 is Rn is Reynolds number, and when the flow is more than, when the Reynolds number is more than 4000, you need to take the coefficient of friction F is equal to 0.316 by Rn to the power of 1 by 4. And we have discussed all these problems here, and flow through long pipe. So when consider the flow through long pipe, the major important issue here is the water level difference between two reservoirs. The water level difference between two reservoirs is equal to the losses, sum of losses. So the water level difference between two reservoirs is equal to capital H, and which is equal to sum of losses here. So losses are entry loss, exit loss, and friction loss. Entry loss, exit loss, and friction loss. And when the pipes are, sometimes you may not get a single pipe of uniform length. In that case, you need to have a different pipes here. Sometimes you may not have a single pipe of having a same diameter, may have a different pipes here. In that case, also the equations are the H. The H is, see here, water level difference between two reservoirs is capital H, which is equal to sum of losses here. So we have exit loss here. We have exit loss here, entry loss here, and friction loss here, and loss of head due to sudden contraction, and again friction loss. Again we have a friction loss here. Again we have a loss of head due to sudden enlargement here. We have contraction, enlargement, again friction loss, and again exit loss here. These are the different losses here. You need to take up actually, and the other equation is the discharge is same. So Q is equal to A1 V1. Q is equal to A1 V1 is equal to A2 V2 is equal to A3 V3. So that is because the same quantity of water which is flowing through the pipe is same. So based on that, you can get the analysis here. And the other one is a compound pipe. So that is another important discussion. So the equivalent pipe, the length of the equivalent. Suppose the three pipes are replaced by a single pipe of length and diameter. In that case, the length is equal to L1 plus L2 plus L3, and deputes the equation, and L by D5. With the help of this equation, you can find out. So this equation is obtained based on the losses for single pipe is equal to losses for all the pipes. So based on that, we have taken. So L by D5, which is equal to L1 by D15. This is plus here. L1 by D15 plus L2 by D25 plus L3 by D35. So this is L1 by D15 plus L3 by D35. This is the definite equation here, and based on that you can find out. So L by D5 is equal to L1 by D15 plus L2 by D25 plus L3 by D35. So based on that you can find out the length, the diameter of equivalent pipe. And when the pipes are connected in parallel, so these are the pipes connected in parallel. So in that case, the equations are the discharge, the quantity of water which is flowing through the main pipe, which is equal to sum of the quantities of water flowing through parallel pipes here. These two pipes are connected parallel, and Q is equal to Q1 plus Q2, and that is one equation. And the losses here in pipe 1 is equal to pipe 2, and HF1 is equal to HF2 if you consider minor losses are neglected. The head loss due to friction for the pipe 1 is equal to head loss due to friction for the pipe 2. And this is a siphon pipe, and it's a bent pipe which is required. when there is a, strong obstruction between the reservoirs A and B. So when there is a hill inside it, when there is an obstruction here, you need to run the pipe along the obstruction portion, and finally, so this is siphon is a long bent pipe here. This is the summit here, topmost portion, and from here to here, this is the inlet leg. Inlet leg is from here to here, and this is the outlet leg from here to here, and this is the height of the summit. So the one equation is when the water level difference between two reservoirs is capital H. So capital H is equal to sum of losses, and you can find out the height of summit by applying Bernoulli's equation at A and C. So this is the siphon. And hydraulic gradient line. So this is the hydraulic gradient line, and this is the total energy line. So the hydraulic gradient line is sum of pressure head and datum head. You take the points of the hydraulic gradient line is the line which gives sum of pressure head and datum head at different points here. So the last point reaches here, and the first point is not well defined. And the hydraulic gradient line is also called piezometric line because it is giving a pressure head and datum head for different points along the pipeline. So this is the total energy line here. Total energy name itself is clear, and total energy is sum of pressure head and velocity head and datum head, and this is the distance between these two is v square by 2g. And here this is the entry loss here. Entry loss is v square by 2g, and here it is exit loss. This is 0.5 v square by 2g, and this is the exit loss here v square by 2g, and in between is the friction loss here. And we have a branched pipe we have discussed it here. The branched pipe, when we have a more than 3 reservoirs, with the help of the pipelines, when you connect more than 3 pipes here, so the entire system is called branching system, and these pipes are called branched pipes. And the assumption here is the velocity of the junction. This is junction here wherein the water comes here and again it is flowing to other direction. So discharge here Q1 is equal to Q2 plus Q3, because whatever the water which is coming out is equal to the water that is flowing into the tank A, B and tank C here. So Q1 is equal to Q2 plus Q3, and you can have another 3 equations by applying Bernoulli's equation at A and D. You can have one equation and Bernoulli equation between D and B, and Bernoulli's equation between D and C. So these are the datum heads here. You can easily solve any problem on the pipeline, provided you know all these equations, etc. So the problem here, you take the problem here. So 3 pipes of length, 800 meters, 600 meters, and 300 meters, and of diameters 40 centimeters, 30 centimeters, and 20 centimeters respectively, are connected in series. So these pipes are to be replaced by a single pipe of length 1700 meters. Find the diameter of single pipe. So 3 pipes of lengths, we have 800, 600, 300 meters. He has given all the 3 lengths here. We have the equation. So this is Dipper's equation. ఓకే అంటే మధ్యలో పవర్ పోయిందండి దాంతో. Okay, so we are student friends. Sorry for the interruption. There was some power problem, and we are discussing this problem here. Three pipes of length 800 meters, 600 meters, and 300 meters, and of diameters 40 centimeters, 30 centimeters, and 20 centimeters respectively, are connected in series. And these pipes are to be replaced by a single pipe. So this is the problem of the equivalent pipe, and you can use Depper's equation. So the total length of the pipe is 1700 meters, which is equal to 800 plus 600 plus 300. So that is 1700 here, and you can use Depper's equation, which is L by D5. L is the length of the single pipe, and D is the diameter of the single pipe. The length is 1700. And L1 by D1 5, L1 is 800 meters and D1 is the diameter is 40, so we can take 0.4. So L1 is 800 meters and D1 is 0.4, so L1 800 by 0.4 to the power of 5 plus, so this is a plus here. So this is again a plus here. So L1 by D1 5 plus L2 by D2 5. Plus L3 by D3 5. So this is L2 here, L2 is 600 meters and D2 is the diameter 2, diameter 2 is 30 centimeters, so you can take 0.3. So 600 by 0.3 to the power of 5 here, and this is the third, the pipe is having diameter 300, so this is 300 by diameter is 20 centimeters, so 300 by 0.2 to the power of 5. So if you take that calculation, and you can find out D is equal to 26.65 centimeters, 26.65 centimeters. The second problem, a main pipe is divided into two parallel pipes. So this is the problem of the pipes connected in parallel, which again form into one pipe, The length and diameter of first pipe is 1900 meters and 1 meter. The length and diameter of first pipe is 1900 meters and 1 meter. And length and diameter of second pipe 1900 meters and 0.8 meters. So find the rate of flow in each parallel pipe. If the total quantity of water is 2.5 meter cube per second. So this is the problem when the pipes are connected in parallel. So here we have a total discharge he has given. Q is equal to 2.5 meter cube per second. So then the equation for parallel pipe is the total quantity which is flowing through main pipe is equal to the quantity of water which is flowing through pipe 1 and pipe 2, because these two are parallel. So for the pipes connected in series, Q1 is equal to Q2 is equal to Q3, whereas for pipes connected in parallel, and summation of the quantity of water in pipe 1 and 2 is equal to total flow in main pipe. So we have equation here, Q is equal to Q1 plus Q2, and Q is 2.5, total discharge is known here, and these two are unknown. So this is A1, V1 and A2, V2. A1 and A2 are known here, so V1, V2 are not known. So we have one equation here, that is HF. So neglect all the minor losses here. We have the friction loss, that is HF is equal to FLV square by 2ZD. FLV square by 2ZD, where F is the quotient of friction, L is the length of the pipe, and V the velocity of the water, and 2 into G is 9.81 gravity meters per second square, and D is the diameter here. So then the other one is the losses in pipe 1 is equal to losses in pipe 2. So the loss in pipe 1 HF1, so which is head loss due to friction from the pipe 1 is equal to F L1 V1 square by 2Z D1, which is equal to F L2 V2 square by 2Z D2. So first you take this equation here, both F and F are same, so you can cancel F here, and L length of the pipe is 1900 meters. So it is also same, the length of the pipe for the pipe 1 and pipe 2, both lengths are same. You can also cancel L, and you have a 2G also common for both the pipes, so you can also cancel that. So this is equal to V square by, V1 square by D1, which is equal to V2 square by D2. So because both two are variables here, so I can take V1 square by D1 is equal to V2 square by D2, because F L by 2G is a constant, L is also constant, and F is also constant. You can take finally V1 square by D1 is equal to V2 square by D2. So we have D1 and D2. So we have D1, D2. D1 is 1 meter here. D1 is 1 meter here, and D2 is 0.8 meters. So we can get the relation between B1 and B2. We can get the relation between B1 and B2. You can get the relation between B1 and B2, and that equation you can use it here. So for example, V2 is, we have some x times V1, so you can substitute here. So this is A1, V1 and A2, V2. You can also convert V2 in terms of V1. So this Q is known here, meter cube per second. Q is known here, and this is A1, V1 plus A2, V2. And here we got a relation between V1 and V2, and substitute V2 in terms of V1 so that you can find out V1. So V1 is equal to Q1, A1. And once you know the Q1, so you can get Q2 also. Very simple problem. Only thing is, need to use this equation HF1 is equal to HF2, and Q1 plus Q2 is equal to Q here. The other problem. So the rate of flow or the crude oil viscosity 0.9 poise, crude oil viscosity 0.9 poise, and specific gravity 0.8 is flowing through a circular pipe of diameter. So this equation is, we can say, Hagen-Poiseuille law. So you remember this equation also, which is Hagen-Poiseuille law, which is equal to pressure difference is equal to 32 mu VL by D square. This is another important equation. Hagen-Poiseuille law for circular pipe. So the pressure difference is equal to 32. So this is 32 here. The equation here is 32, and mu is the dynamic viscosity. So mu VL. So mu VL by gamma D square or D square. So P1 minus PT by W is the pressure difference here, which is loss here. So HF is equal to P1 minus PT by W, which is also equal to 32 mu VL by gamma D square or B square. Suppose if you take only P1 minus P2 alone, it is equal to 32 mu. Mu is the dynamic viscosity, and this V is the average velocity, and this is the length of the pipe, and D is the diameter of the pipe here. This is also, this equation is called Hagen's equation, Hagen-Poiseuille equation. So now he has given crude oil viscosity 0.9 poise here. Once again, you need to remember the relation between system of units, one system to other system. So the velocity is 0.9 poise here, and we have a viscosity is 0.9 poise here, and as you know, the viscosity from the fundamentals of fluid chapter, fluid properties, the units are 1 Newton second by meter square is equal to 0.102 kg/4 seconds per meter square is equal to 9.81 poise. Suppose you want to convert poise into MK system, so 0.9 by 98.1, then we'll get kg/4 seconds by meter square. Need to remember the system of units here, because we have discussed that in the first class, and the same information now it is required for you to solve the problem. So now we can have the specific gravity is 0.8 here, and the diameter is 8 centimeters. So diameter is 8 centimeters. You can take 0.08 meters, 0.08 meters, 0.08 meters, and of length 15 meters. So length is 15 meters here. Length is 15 meters here, and calculate the difference of pressure. At the two ends of the pipe. If the rate of flow of oil is 4.17 into 10 power minus 3 meter cube per second. So he has given complete data here, but only thing is need to remember the equation P1 minus P2, which is equal to 32 mu VL by D square. So the average velocity you can find out, which is equal to Q by A. Q is 4.17 into 10 power minus 3. Q is equal to 4.17 into 10 power minus 3 by A. A is the cross-section area. And the cross-section area's diameter is 8 centimeters here, pi by 4, and the diameter is 0.08, so 0.08 meters. So find out the discharge by area, which is velocity Q is equal to AV. This is a continuity equation. From that, the velocity is 0.82 meters per second. Now we have the value of velocity 0.82 meters per second, and the other value is P1 minus P2 is equal to 32 mu L by d square. So P1 minus P2 is the pressure here, and 32 is value known, and dynamic viscosity you need to take not 0.9, it is required to take 0.9 by 98.1. 0.9 by 98.1 kg force seconds by meter square, the unit, and the velocity here is 0.82, velocity here is 0.82, and length is 15 meters, we have this value, and the diameter here is 0.08 square. So use this value, use the values here and find out the pressure difference of pressure, which is equal to 566.98 kg force per square meter. This is very simple, provided you know the pressure drop. This is pressure drop is equal to 32 into mu L by d square. The other problem here, the rate of water through a Harjan pipe is 0.3 meter cube per second. The diameter of the pipe is channel enlarged from 25 centimeters to 50 centimeters. The pressure intensity in the smaller pipe is 1.4 kg force per centimeter square. The rate of water through flow of water through a Harjan pipe is 0.3 meter cube per second. So the diameter of the pipe is suddenly enlarged from 25 centimeters to 50 centimeters. So the pressure intensity in a smaller pipe is 1.4 kg force per centimeter square. Determine the loss of head due to shunt enlargement and pressure intensity in the larger pipe. So this is the problem here. This is the problem due to the problem due to shunt enlargement. So you can take shunt enlargement. So sudden enlargement from 25 centimeters, 50 centimeters, the pressure intensity in a smaller pipe, has given. So you can use straight away the equation here, equation here, so that you can find out the problem in no time here. So the equation here. So the equation is, as you know, the head loss due to sudden enlargement is V1 minus V2 whole square by 2Z, V1 minus V2 whole square by 2Z, and V1 is the velocity 6.115 meter per second, and V2 is the velocity 1.52 meters per second. So here V1 minus V2 whole square by 2Z. So because we have a discharge here, so we have the discharge is 0.3 meter cube per second. The rate of flow of water through a Harjan pipe is 0.3, means it is a discharge here. So now the discharge is known. So B1 is equal to Q by A1. So Q is equal to 0.3 and the area is 25 centimeters. So it is reduced from 25 to 50. So B1 is equal to, so we have the discharge here 0.3 and diameter is 25 and diameter is 50 here. So D1 25 and D2 50 and discharge is 0.3. So here this is V1 equal to Q by A1. So Q is equal to 0.3 and A1 is pi by 4 into 0.25 whole square. You can get V1 what is equal to 6.115 meter per second, and V2 is equal to again Q by A2 0.3 by pi by 4 into 0.5 square, which is 1.52 meters per second. 1.52 meters per second. So the HL is equal to V1 minus V2 whole square by 2Z. So which is equal to V1, as you know, V1 is 6.115 minus 1.52 whole square. So whole square by 2Z. So which is equal to 1.07 meters. So HL is equal to V1 minus V2 square by 2Z. This is 1.07, and because it is a Harjan pipe, so you can take Z1 is equal to Z2. Apply Bernoulli's equation here. Apply Bernoulli's equation, which is P1 by W plus V1 square by 2Z plus Z1, which is equal to P2 by W plus V2 square by 2G plus Z2 plus HL. So now Pt is equal to, so find out here P1 by W, the pressure is known here, pressure index in the smaller pipe is 1.4 into 10 power 4, so here we can take, this is 1.4 into 10 power 4 in kg force per meter square by 1000, W you can take 1000 here, MK system, and this is B1 is 6.115 square by 2G, and Z1 and Z2 are zeros, you can cancel Z1 and Z2. So P1 by W plus V1 square by 2G, which is equal to P2 by W. P2 is not known here, and B2 is 1.52 meter square by meter square, meter by second, 1.52 whole square by 2G, 2 into 9.81, and Z2 is equal to Z1. So here you need to take the losses here. So whenever we take Bernoulli's equation, you see that if we have losses, you need to consider the losses also. And some of the students, they are forgetting this HL, and straight away they are getting the value P2 here. Without the value of HL, the answer is wrong. So you need to take HL here. Now the value of HL, the head loss due to sudden enlargement, which is equal to 1.07. So HL is equal to 1.07 and Z1, Z2 are 0. All the values are known except P2. We can find out the value of P2, which is equal to 1.47 into 10 power 4 kg force per square meter. Simple problem here. So this is the head loss due to sudden enlargement problem. Again, if you see here, this is another problem. A 200 mm diameter of the pipe reduces in diameter abruptly. So abruptly means sudden. Sometimes the students are confusing. What is this abrupt like this? So this is abrupt means there is a sudden change in cross section area. So when there is sudden reduction in diameter of the pipe, in other words, you need to apply the head loss due to sudden contraction. And he has given diameters here. One is 200, the other one is 100. So based on that, you can find out velocity here. He has given the pipe discharge. Pipe carries water at 25 to 10 power minus 3 meter cube per second. Then calculate the pressure loss across the contraction here. So 25 to 10 power minus 3 meter cube per second. Again, this is 25 to 10 power minus 3 meter cube per second. Here we have discharge here Q. Q is known here, and diameter D1 is known here, and diameter D2 is known here. So you can find out V1 here. V1 is equal to Q by A1. So Q is 25 to 10 power minus 3, and A1 is, you can convert 200 into meters here into 10 power minus 3. So that means 0.2. So 5 by 4 into 0.2 whole square. So that is, you can get V1, which is 0.795 meters per second. And again V2 here, V2 is Q. Q is 25 to 10 power minus 3. And A2 is again 5 by 4, 100 into 100 mm converted to meters here, 0.1. So 100 by 5 by 4, 25 to 10 power minus 3, the discharge, that divided by 5 by 4 into 0.1 whole square. So V2 is equal to 3.18. So this is simply from continuity equation, Q is equal to A1, V1 is equal to A2, V2. Then head loss due to shunt contraction, now it is K V2 square by 2Z is equal to 0.22 meters here. So K V2 square by 2G is equal to 0.22 meters here. Then what is the value of constant K, which is equal to 1 by Cc minus 1 whole square, where Cc is the quotient of contraction. He has given take Cc is equal to 0.6. So then substitute the value of 0.6 here, 1 by 0.6 minus 1 to the whole square, 1 by Cc minus 1 square. So this is the value of K, and we have the value of Cc is equal to 0.6. You can find out K here, and K into V2 square by 2Z, and where V2 is equal to 3.18. So this is V2. The problem here is some of the students are taking V1. So one important aspect here is when you want to find out the head loss due to shunt enlargement, K is equal to V2. V2 means the velocity after enlargement, after contraction. You need to take velocity after contraction, not before contraction. So this is no doubt Kv square by 2Z, but this V is velocity of water after contraction. That's why it is V2 here. Some of the students are doing mistake here. That's why I'm stressing. So K is equal to 1 by Cc minus 1, the value, and sometimes in the absence of Cc, you can also take K is equal to 0.5. So now we have V2 here, and this is the value here obtained, and V2 is 3.18. You can find out here. G is 9.81, so this is equal to 0.22 meters here. So now we have all the values here, and P1 is not known and P2 is not known, and because it is a horizontal, you can take Z1 is equal to Z2. So V1 square by 2Z is not known, and V2 square by 2Z. V1 is P1 is not known here, you can leave it as it is, and V1 is 0.795 square by 2Z, 9.81, and Z1 is equal to Z2, you can cancel Z1, Z2, and P2 is also known, and V2 is known here, V2 is 3.18 square by 2 into 9.81, and Z2 is 0, and HL is 0.22. You need to substitute the value HL here. Whether it is a sudden expansion or contraction, try to remember that you need to use HL here. When you go to the gate problems, also you need to use HL, which he has given in the problem. So now we have used HL here, and W is known here. So the pressure difference, pressure loss, P1 minus P2, which is equal to 0.707 into 10 power 3 kg force per meter square. 0.707 into 10 power 3 kg force per square meters. Now we'll go to objective question. So now objective questions now. Yeah, the question number 1, the flow through a pipe, the transition from laminar to turbulent flow, transition from laminar to turbulent does not depend on. So it totally depends on Reynolds number. Suppose if you see the flow through a pipe from laminar to turbulent, the transition from laminar to turbulent. So because in the transition flow, it all depends on the Reynolds number. For example, you know, when the Reynolds number is less than 2000, so it is less than 2000, it is laminar flow, and if it is more than 4000, it is turbulent flow. వస్తుందమ్మా ఎవరో రావట్లేదని చెప్పి ఫోన్ చేశారు వస్తుందా ఓకే ఓకే అందుకే రైట్ రైట్ okay my friends and I received a call that it is not coming, that's why I am checking with organizers. So it seems it is coming and it is on now. So here the discussion for this is the transition flow for which laminar we have a laminar flow. Laminar flow means Reynolds number less than 2000, and when the Reynolds number is 4000, it is turbulent flow. So Reynolds number is 2000 4000, it is transition flow. So that means the transition from laminar to turbulent entirely depends on Reynolds number. Reynolds number is rho v d by mu. So there is some ambiguity here, but you can take the answer D here. But strictly speaking, it depends on Reynolds number, which is the rho v d by mu here. The second one, the velocity profile in a fully developed laminar flow in a pipe of diameter D is given by U is equal to U0 or something like that, where the radial distance from the center, if the viscosity of the fluid is U, the pressure drop across the length L of the pipe. We have an equation here. As earlier I told you, this is 32 G.V.R by D square. So 32 G.V.R by D square. So you can close to that, you can take the answer D. This is Huygens-Poiseuille's law, and this is system. The answer is D here, 2D. And a fully developed laminar viscous flow through a circular tube has the ratio of maximum velocity to the average velocity. So this is a maximum velocity to average velocity is 2 here. So the answer is C here. Try to remember that. It is not a difficult one, not necessarily to derive the relation. So the maximum velocity to the average velocity 2. It is for laminar viscous flow through a circular tube. Ratio between maximum velocity to average velocity. Similarly, for the laminar flow through a long pipe, the pressure drop per unit length increases. So the pressure drop per unit length, this is dP by dL, so which is equal to even 32 μl by d square, and you can convert 32 it's the same equation here, you can convert here. So this is also equal to 128. In place of V, if we take the discharge, and V is equal to Q by A, and we have a square here and square here, and the indirectly it is 128 mu. These all the equations are same. Only thing is in place of V, he has taken Q by A. In place of V, he has taken Q by A, and Q he has given, and A is a pi by 4 d square, and pi by 4, this is a pi here, and 4 he had there. That's why. And this is 32 into 4, 32 mBl by d square. So this is 32 into 4, pi d square of 4. He has converted velocity into Q by area. So this is like that. So it is proportional to, so this is proportional to 1 by d4, and d4 means area square. So pi d square by 4, and d square is area square. So this is inversely proportional to square of cross section area. So the pressure drop is 32 μl by d square, and V can convert to Q by pi by 4 d square, and 4 into 32, this one, the same equation, but in place of V has taken Q by A, because you need to have a relation with d square, and now as it is d4, and the area is pi d square, and pi d square and d square and d square, so this is A square. So this is inversely proportional to square of cross section area. The answer is D here. In a fully developed laminar flow and circular pipe, the head loss due to friction is directly proportional to, this is 32 μBl. The same equation, this is both are same, and in place of V has taken Q by A. So Q by A means we have pi d square by 4, and 4 into 32 we get 128. Both equations are same. So 32 μl by d square, and this is this V is the average velocity. That's why he has taken mean velocity, which is that is true here. The answer is true. And gate 3. The problem 3 here, the fluid is flowing with an average velocity of V, average velocity is average velocity of V through a pipe of diameter D over a length of L. The head loss is given by HF is equal to FLV square 2ZD. So he has given the head loss due to friction, which is FLV square by 2ZD, the friction factor. So friction factor for laminar flow, he mentioned that the flow is laminar. So the answer is 64. The answer is 64 by RE. 64 by RE. So 64 by RE. So the water flows through the next one, the water flows through a 0.6 meters diameter, 1000 meters long pipe from a overhead tank to a village. So the answer for the third question is 64. The slight question. So relation between the friction factor and Reynolds number when the flow is laminar, F is equal to 64 by Rn. So question number 4, water flows through a 0.6 meters diameter, 1000 meter long pipe from a 30 meters overhead tank to a village. Find the discharge in liters at the village at ground level, assuming the friction factor F is equal to 0.04 and ignoring minor losses due to bends, etc. So he has given the coefficient of friction is equal to 0.04 and the diameter is 0.6 meters and length of the pipe is 1000 meters and 30 meters overhead tank. So head available here. And we have the equation HF is equal to FLV square by 2ZD. F is the coefficient of friction is 0.04 and L is the length of the pipe 1000. V is the velocity not known and 2 G is 9.8 and the gravity is not known here and diameter is 0.6. So delta H means the head without losses here. The head without losses. The total head available is we have the total head availability 30 meters here. So he has given total head availability 30 meters, and HF is head loss due to friction. So head loss due to friction is the value here. So that we can get H minus HF, 30 minus HF. This is also in terms of so 30 minus HF. This is also in terms of V square. So this you can also take in the normal equation. So the velocity, as you know, the velocity is equal to square root of 2gh, v is equal to square root of 2gh, where h is the head available, the velocity. So the velocity is not known. You can also convert delta h in terms of velocity so that you can find out velocity here. So v is equal to square root of 2gh, the common equation, and delta h is equal to v square by 2g. So this is the common equation. Delta h is equal to v square by 2g, which is equal to 30 minus hf, which is the delta h, and this is the equation. So this is V, this is in terms of V here, this is also in terms of V, and so that you can find out the velocity V, which is equal to 2.95 meters per second. I am repeating here, slightly important here. One HF is FLV square by 2ZD, FLV square by 2ZD, so therefore delta H is equal to H minus H, which is equal to 30 minus H. Delta H is the head without loss here, H minus H, so the total head available is 30 minus HF. This is one side, and let us say right hand side. So delta H you can also find out from the general equation, generalized equation, that is V is equal to square root 2G delta H, or delta H is equal to V square by 2G. So now V square by 2G is equal to 30 minus HF, which is equal to this value, and only unknown is V here, so that we can find out the velocity V here. So once the velocity is known, velocity is 2.95 meters per second, then 2.95 into area is pi d square by 4. And the discharge, he has also find out the discharge here, find the discharge in meters. So now it is point B into A here, 0.834 meter cube per second. Discharge area into velocity pi into d square by 4. So this is the answer here. So the other problem, so water at 25 degrees centigrade is flowing through a 1 kilometer long GA pipe of 200 mm diameter at the rate of 0.07 meter cube per second. If value of the Archie's friction factor for this pipe is 0.02 and density of water is 1000 kg per meter cube, the pumping power required to maintain the flow. And the power is, as you know, this is WQH, W is rho into Z. So rho G QHF is the generalized equation for obtaining power. So find out HF here. So HF is equal to FLV square by 2ZD. And we can also convert this V into Q by D. So instead of using Q is equal to AV and find out V, you can straight away convert V in terms of Q, and so that you can straight away apply those values in the equation. So V is equal to Q by A. So V square is Q square by A square. So Q square by A square is Q square. A square is pi D square. So pi square. And D4 we are also having D here. That's why there is a D phi here. So now the equation is 8 FL Q1 square by pi square G D phi. Same, these two are same. Only in place of V, he has taken Q by A. Q is equal to AB. So now the equation is F is known here. So F is 8 into 0.02. 8 into 0.02. L is 1000. L is 1000, and it is discharge he has given 0.07. 0.07 meter cube per second. 0.07 square. So 8 FL Q1 square, and this is pi square, and G is 9.81, and D here is diameter here 200 mm. So convert into meters here, 210 power minus 3.2 meters. So this is 0.2 to the power of 5 here. This is to the power of 5, which is equal to 25.30. So HF is equal to 25.30 here. Now this is the equation here. Rho G into Q into HF, and rho is 1000 kg per meter cube into 9.81. So I can get in newtons here. And 0.07 Q is 0.07 meter cube per second, and this is meters here. and this is watts here. So this is the equation here, and the answer here is 17.4. If you get this multiplication, and it will be getting 17.4 kilowatt. So watt means by 1000, so that we will be getting 17.4 kilowatt. So the other problem here in Hagen-Poiseuille flow of viscous fluid, one of the following pairs of forces strike a balance. Hagen-Poiseuille. So as you know, the equation here you can see here. You can see here the pressure force and viscous force here. So the P1 minus P2 by W, which is equal to 32 μVL by gamma d square. So this is the Hagen-Poiseuille, and as you know, this is HF, given HF is equal to P1 minus P2, which is 32 μVL by d square. You can take gamma and gamma here. This is a gamma, and this is also equal to gamma. Gamma is equal to rho g. So both are same here. P1 minus P2, 32 μVL by d square, or P1 minus P2 by rho g, 32 μVL by d square. Both are same. And this gamma and rho g both are same here, which is equal to head loss due to friction. So HF is equal to P1 minus P2 by W, which is equal to P1 minus P2 by W or gamma, which is also equal to 32 μVL by gamma d square. So suppose if you see here, this is a pressure force here, and this is viscous force here. So this depends on pressure and viscous force. The answer for 1, B, that is pressure force and viscous force. The Reynolds number of a flow is the ratio. This is the basic definition of Reynolds number. Reynolds number definition is inertia force to viscous force. The definition of Reynolds number, it is a ratio of inertia force to viscous force, and rho by mu. Definition itself is inertia force to viscous force. The answer is C. For 2 it is C. The other important question, the dimensions of a pressure gradient. In a fluid flow or so dimension analysis is also required to convert into MLT system. So he has given MLT system here. So the pressure gradient, as you know, it is dP by dx, which is equal to Newton by meter square by meter. The unit of pressure is, as you know, Pascal is Newton per meter square. So Newton per meter square divided by meter, that is Newton per meter cube. Then how will you convert into dimension analysis? So Newton is kg force here, F is equal to MA. So Newton is kg force, F is equal to MA. So F is equal to MA mass in kgs and meters by second square. So this is a mass system and this is acceleration. So this Newton, F is equal to MA. So this is Newton here, kg mass by second square by meter cube. Meter cube is meter here, Newton by meter cube. So now it is meter second square, and you can cancel here. Finally, this is kg by meter square second square. So kg you can take m here. And meter square is L square. Meter square is L square, and this is T square. So now it is m L minus 2 T minus 2. So the answer is C. This is a simple question. You can easily answer. And we have a very quick break here because we have wasted some time due to power failure, etc. I will be back within 5 minutes and take water and again be ready. I will be back in 5 minutes. So yes, student friends, welcome back. And we are discussing very important questions here. You have followed this, the dimensions of a pressure gradient in a fluid flow, or the answer is C here. So this is a dimension system, and it is very easy here. The dp is the pressure is Newton per meter square, and distance is meters and Newton per meter cube. And the force you can convert to mass into acceleration. Mass into acceleration is kg mass here, and acceleration is meters per second square. So this is kg per meter square per second square, and kg in m, and meter square is L, and second square is T. So ml minus 2 and T minus 2. Another important question for study incompressible laminar flow between two infinite parallel stationary plates, the shear stress variation is. So in general, if you study the fluid mechanics of any Sternberg, Modi and Shea, Bansal and fluid mechanics, Mundal, etc., the shear stress, this is the distribution of shear stress here, distribution of shear stress here, it is varying linearly. So the velocity distribution is very linearly, and exactly at the center it is 0. So if you see here, this is the distribution of shear stress. So the shear stress is maximum at the boundaries, maximum at the boundaries. If you draw the shear stress distribution for the pipe flow between two and finite parallel stationary plates, the shear stress variation, if you could draw, then the equation is maximum shear stress you can obtain here at the boundary, and it varies linearly and has a 0 value exactly at the center. So the students are confusing, they are taking 0 and they are taking a parabolic variation, and they are giving maximum here. So this is the shear stress variation for laminar flow, incompressible laminar flow between two parallel plates here, and both are stationary. And the answer here is a linear variation but with zero value at the center. This is also more or less the same question. The shear stress in a fully developed laminar flow in a circular pipe. More or less the same question but different years. And once again, I told you that other way of asking. So this is laminar flow in a circular pipe. The resistance against laminar flow due to viscosity for the resistance is maximum. So that is different. This is different here. This is for the circular pipe. In a circular pipe, and suppose if you see here, this is between stationary plates and this is rigid and rigid. And now this equation is here. If you see here, the shear stress varies linearly with zero at the center, but this is zero at the center and maximum at the pipe wall. Similarly. So now this is maximum at the pipe wall, and earlier he has given zero at the center for the other question. Same question he has asked that this is maximum at the pipe wall. Need to mention that the shear stress is zero at the center and maximum at the pipe wall. The answer is C here. More or less a similar type of question. The other question here, the flow rate of fluid on a small diameter tube is 800 mm³ per second. The length and the diameter of the tube are 2 meters and 0.5 meters respectively. The pressure drop in 2 meter length is equal to 2 megapascals, the viscosity of the fluid. The pressure drop he has given megapascals. Megapascals is 2 into 10 power 6 kilopascals. And he has given the rate of flow, etc. And he has given density of fluid is 1000 kg per meter cube and the discharge is 800 mm³ per second. So you need to convert, you need to be comfortable with the system of units. You need to be comfortable with system of units. So 800 into 10 power minus 9 meter cube per second, that is also equal to length of the tube is equal to 2 meters. So diameter of the tube is 0.5 meters. So the discharge in terms of meters, 1 mm, as you know, it is 10 power minus 3 meters. So 10 mm³, 10 power minus 9 meter cube per second. That is discharge here. The length of the tube is 2 meters and the diameter of the tube is 0.5 mm. So again, you can convert into 0.5 into 10 power minus 3 meters. So the pressure drop he has given 2 megapascals. 2 megapascals is 2 into 10 power 6 Newton per meter square. So Huygens follows the equation. The pressure drop, as you know, delta P 32 μ/r by d square. So this V you can take is equal to Q by A, and Q is Q and A is pi d square. So pi d square by 4. So here the 4 times 32 128. These two are same except in place of V he has taken Q by pi by 4 d square. So this is 128 mu QL by pi d4. So which is 2 into 10 power 6 is equal to 128 mu into 800 into 10 power minus 9 into 2 by pi into 0.5 into 10 power minus 3 to the power of 4. So the answer is equal to 0.00. So here we have the value here. This is the discharge. Value is known 810 power minus 9 and the length is known here, and this is diameter is 0.5 into 10 power minus 3. Straightforward simple problem here, but only thing is you need to write the units properly. So it is 0.09192 Newton second per meter square. The answer is C. So water pumped at a steady uniform flow rate of 0.01 meter cube per second to a horizontal smooth circular pipe of 100 mm diameter. He has given the Reynolds number is 800, that is laminar flow less than 2000 and G is 9.81 meters per second square. The head loss in meters up to 1 decimal place per kilometer length due to friction could be. This is the problem. He has given length of the pipe. Length of the pipe is 1 kilometer. Length of the pipe is 1 kilometer, and the Reynolds number is 800. That means as it is less than 2000, as it is less than 2000. So this is HF is equal to Vapor viscosity 2CD, which is also equal to, in place of V we can take Q by area and Q square by 5 square. So this is both are same here, but in place of V he has taken Q by A. So Q by A is Q, area is pi by 4 d square. So 8FL Q square by pi square GD5. So then flow through circular pipe. If Reynolds number is less than 2000, you can side away take relation between F and Rn. So F is equal to 64 by Rn and 64 by 800, which is equal to F is equal to 0.08. So now we have the equation here HF, which is equal to 8 into 0.08 into 1000, 0.01 whole square by pi square into 9.81 into 0.1 to the power of 5. So 8FL Q square, so F is 0.08 and L is 1000, Q is 0.01 whole square and pi square 9.81 into 0.1 to the power of 5, so which is equal to 66.1 meter. So answer is 66.1 meter. Straightforward problem. So find out F value and use Darcy's equation, Darcy-Weisbach's equation, find out HF. Another question here in the gate examination, these are all the problems of gate, problems given in gate. The bulk modulus of water is 2 into 10 power 4 kg force per square centimeters. In other words, it is also equal to 19.62 into 10 power 8 Newton per meter square. Then water hammer wave is equal to through a rigid pipeline is equal to, just straight away remember the equation, C is equal to square root of K per rho, and this is a famous equation, K per rho, and K is 19.62 10 power 8 Newton per meter square, and this is 1000. So use bulk modulus of velocity Newton per meter square and mass density in kg per meter cube. So this is kg per meter cube is in SI system. SI system, the unit of mass density is kg per meter cube. It may be confusing here again. Mass density of water is MSL per meter cube. Both should be in SI system. The bulk modulus of velocity of water Newton per meter square. This is Newton per kg per meter cube is the mass density in SI system. So finally, the solidity of the wave is 1400 meters per second. Just remember the equation. Also, it is required to use them in SI system only. The second question, the loss of energy at the exit of a submerged pipe is. So exit pipe, as you know, at the exit level, the loss is V square by 2Z. So without any issue, without any problem, straight away you can give the answer A. Answer is equal to A, because we have already given that the exit loss of head at the exit is V square by 2Z. You can straight away give A. No explanation is required for this. So eddy viscosity, if you remember the turbulent flow, the turbulent flow is because of the formation of eddies. If you remember, go back to your Reynolds experiment and basic definition of turbulent flow. The turbulent flow is when the flow is flowing irregular, erratic, and intermingling of fluid particles and formation of eddies, all these things. So any turbulent which always refers, you can have eddy viscosity here. Suppose if you see all A, B, C, this is all different, but D is the apparent viscosity due to turbulent nature of the flow. So this eddy means it is obviously D. So also D here. What are the explanation we have? So eddy viscosity is an apparent viscosity due to turbulent nature of the flow. You can straight away, if it is eddy, you can correlate to turbulent. So the answer is D here. The other problem, water is pumped through a pipeline to a height of 10 meters at the rate of 0.1 meter cube per second. Frictional and other minor losses are 5 meters, then the power of the pump in kilowatt is required. Then straightforward problem here. Pipeline height 10 meters, H is 10 meters, and the discharge is 0.1 meter cube per second. And it has asked to find out the power of the pump, and also the minor loss also has given. Need not necessary to calculate the losses here. He has given losses here. Then the total head available, the head plus actual head plus losses here. You can take the total head and the power equation is WQH, where W is rho into Z. So rho into G is 9.81, 9.81 here, rho G Q, and H plus HR into kilowatt. So this rho G is equal to W means small w, or specific weight. Specific weight is equal to mass density gravity, and this is specific weight here, which is equal to 9.81 kilonewton per meter cube here. You should be more careful while giving units here. 9.81 means 9810. Gamma is 9810 Newton per meter cube in SI system, which is also equal to 9.81 kilonewton per meter cube. Whatever the fundamentals you learned in initial classes, you might have learned in our circuit of fluid mechanics. Now you are getting those fundamentals now, right now, even in pipe flow problems. So if you are not able to give a correct value to the gamma here, the problem will be wrong, even though you know the equation, etc. So now this is 9.81 is kilonewton per meter cube, and discharge Q is 0.1 meter cube per second. He has given HF and H. H is 10 meters here, and the losses he has given 5. So 10 plus 5, so 9.81 into 0.1, 15. So this is equal to around 15 kilowatt. So I need to use in kilonewton here to get in kilowatt. This is another straightforward problem. The friction factor for a turbulent flow in smooth pipes varies. So when the flow is turbulent, when the Reynolds number is less than 4,000, then the friction factor F is equal to 0.316 by Rn to the power of 1 by 4. The same question was posed to me when I was attended my assistant professor interview at JNU Hyderabad, early days. But it is a very important question. So this Reynolds, friction factor for turbulent flow is equal to Rn, is equal to 0.316 by Rn to the power of 1 by 4. So you can see here, this is inversely as a 1/4 power of Reynolds number, 1/4 power of Reynolds number. So you can straight away give answer which is D, inversely as 1/4 power of Reynolds number. The other equation, civil head phone చేస్తున్నాడు లాస్ట్ వన్ అని చెప్పి ఈ బొర్రా విజయ్ కుమార్ గారు ఫోన్ చేస్తారు. So the other problem here, the stresses that arises due to fluctuations in the velocity components in turbulent flow are. So here the answer is Reynolds stresses. The answer is Reynolds stresses. Yes, the head loss due to sudden expansion. Head loss due to sudden expansion, no. I have given the head loss due to sudden expansion is V1 minus V2 whole square by 2Z. So try to remember the equation so that you can straight away give answers here. The answer for 7 is D. So V1 is velocity before expansion and V2 is velocity after expansion. This is sudden. So the velocity head loss due to sudden expansion is expressed by, so this is sudden, V1 minus V2 whole square by 2Z. The explanation here, definitely, you can straight away give the explanation, the answer is D here. Another simple problem here, in a siphon as shown in figure below, assuming ideal flow, pressure P. So go back to your fundamentals, remember our fundamentals, what happens when you go out, you have given positive sign, when you go down, when you go up, you have given negative sign. What is the reason for that? So while writing the gauge equation in the pressure chapter, if you remember, not doing anything with simple common sense and logic, you can straight away give the answer for this question. Not necessary to apply Bernoulli's equation here and here and find out the answer. So here the answer is, and he has asked you to find out the pressure at B. So that means the pressure at B, this is a siphon pipe and this is the summit here. We have a summit here. The topest portion is summit here and here the pressure here. And that means the point at B is high level compared to point at A. Then compared to PA, the pressure PB is at high level or less level. So when you go up, the pressure should decrease. When you go down, the pressure increases here. So that means the PB, he is asking here, we have the value of PA, he is asking here, that means the pressure will be less. So the value of PB will be less than PA. So because as you are going up, the pressure decrease, so the PA will be more compared to PB. So the PB is less than PA. The answer is B. Straight away you can take B. Otherwise you can have the equation here. And it has also given shortcut. As we move up, the pressure will decrease. And point Y is above HCl and it is a summit. So the pressure at this point is least. Or you can apply straight away the equation here, Bennett's equation between A and B. And the velocity here. So the velocity here is VA is equal to VB. The velocity here is VA is equal to VB. As the pipe is having same diameter, so you can take velocity VA and VB, both are same. So you can cancel VA by VB and VB by 2 square. So these two you can cancel. And PA by W plus ZA, which is equal to PB by W plus ZB. This is the equation here. So ZA and ZB, if you take ZA here, this is ZB here. So ZB is high level compared to ZA. So ZB is more than ZA. When ZB is more than ZA, the PB should be less than P. Otherwise, this equation cannot be satisfied. So this is the theoretical, expression. With the help of the mathematics, you can prove that PB is less than PA. This is the understanding. So when the pressure, when you are going up, the pressure should decrease. So straight away can, instead of taking steps, straight away can give the pressure B is less than PA. The answer is B. Now the question is 9. The flow in a pipe can be expected to be turbulent when the Reynolds number based on mean velocity and pipe diameter is. So when the flow is turbulent, when the Reynolds number is more than it is turbulent. It has not given any value. Actually, strictly speaking, 2000 to 4000 transition flow, but only question which is close to Reynolds number less than more than 4000 is C. You can give the answer C. But you can see that Reynolds number less than 2000 laminar flow. And in between it is a transition flow, 2000 to 4000 transition flow and more than 4000 turbulent flow. But option C is very close to the correct answer. That's why you can give C. So don't give that answer. The problem has no answer. But greater than 3000 means it is also greater than 4000. You can also think logically and you can give answer C here. But if it is more than 4000, this is absolutely okay and you can straight away give answer C. Even if it is more than 3000 and there are no other answers which are close to this value, suppose one answer is more than 3000, one answer is more than 4000, you need to give more than 4000, not more than 3000. But out of all the four, this is quite close to the answer, so that you can take 9, the answer C. The friction factor of a laminar flow in a circular pipe is proportional to, once again, F is equal to 64 Rn. So F proportional to 1 by Rn. So this is inversely proportional, square root of inversely proportional. You can straight away give with the help of this simple equation, the friction factor of a laminar flow, this is for laminar flow, is inversely proportional to Reynolds number. While deriving an expression for the loss of head due to sudden expansion, in a pipe, in addition to the continuity and impulse moment equation, one of the following assumptions are made. So once again, this is the answer you can take. So the last term here, you can simply here, this is due to expansion here, this is due to expansion here. So in the derivation of this, you can straight away take the head loss due to friction. The head loss due to friction is equal to the head loss in heading motion. So we have different losses here, but we have taken the head loss due to the sudden enlargement. In other words, the head loss in heading motion, you can straight away take head loss due to friction. This is assumption we have made for deriving the expression. These are the steps here. So you can, if you see here, we have taken, this is eddy loss. The loss term HR is taken as eddy loss, which is equal to head loss due to friction in the derivation. If a single pipe of length and diameter D to be replaced by 3 pipes of same material and same length, So this is a problem under equivalent pipe. The problem under the equivalent pipe, it has given length and diameter, length L and diameter D, is to be replaced by 3 pipes of same material, same length and equal diameter here, to convey the same D and D are related. So then there is a straightforward equation here. We can also take for pipes in parallel, so we can cite an equation here. The equation is D is equal to D by N to the power of T by 5. So here capital D, single pipe diameter, and 3 pipes of same diameter is small d, which is less than capital D. So small d is diameter of 3 pipes of same material. So we have 3 pipes of diameter d of same material, same length and diameter same for 3 pipes, and it has also find out single pipe. We want to replace that with a single pipe of length and d. So what is the relation between d and d? So the actual relation is D is equal to D by N to the power of 2 by 5, where N is number of small pipes of diameter D. So you can straight away, remember this equation and take the value, because the number of pipes are 3 here, 3 pipes here, N is 3. So D is equal to D by 3 to the power of 2 by 5. So this is answer is A. This is 2 by 3, very close to that, but this is 2 by 5. So D is equal to D by 3 to the power of 2 by 5. Very, very interesting problem here. 3 reservoirs. It's also once again common understanding, general knowledge, not necessary to take a lot of analysis here. A common understanding here. So now we have reservoirs ABC here, and the head available, this is 180 meters here. So here it has given 200 meters here, the head available here is 200 meters here, energy level available, total energy, and here it is 160 here, somewhere here this is 160, and here the energy level is 180, and here the energy level is 140. Just to see all the 4. And he has asked to get the relation between Q1, Q2 and Q3, Q1, Q2 and Q3. Seems all are okay. But normal equation may think that Q1 is equal to Q2 plus Q3, not like that. So see here, so this is 200 meters here. So this is 200 meters here, and this is 160 meters here. Total head. So the flow direction depends on the total head or energy level. So when the energy level here at A is more than energy level at this point, the flow is from A to J. The energy level is 200 here, it is 160 here, then the flow is from A to J. So that means the Q1 quantity of water which is flowing from A to J. Then at this location, if you see here, what exactly happens at the junction? So this energy level is 180. The energy level at point B is 180 and this is 160. That means from here to here this is coming down. From here this is not going up. Suppose if the water is going up, you can take Q1 equal to Q2 plus Q3. This is coming down. So this is 180 here, this is 160. The total energy level available is 160 and total energy level is 180. So 180 to here, 180 here is 160. So again the flow is from B to J. So that means the Q2 is coming down. So Q1 is going this direction. So you have a combination of Q1 and Q2 here. So Q1 and Q2 will join here. Then you see here, this is 160. The head level is 160 and this is 140. That means the flow is from J to C. The flow is coming down. So then what happening here? Whatever the quantity of water which is flowing from A is coming down here. Because it is 200, it is 160. Q1 is coming down. And Q2 here, this is 180 and this is 160. Q2 is coming down. So there is a combination of Q1 and Q2 here, Q1 and Q2 here, and both it is going down. So because it is 160 and 140, so the equation is Q1 plus Q2 is equal to Q3. Normally people think that straight away they will give B, so which is wrong. So a paper set will be given such a way that it is looking simple, but there is some intelligent way of asking the question here. So this depends on energy levels here, So this should be Q1. This is also coming down. Q1 plus Q2 is equal to Q3. That is the equation. So the same explanation here. This is another interesting question here. For a steady incompressible flow through a closed conduit of uniform cross section, the direction of flow will always be. For a steady incompressible flow through a closed conduit of uniform cross section, direction of flow will be. That's a very important question, and it requires understanding of the total head. What is total head? The total head is P by W plus V square by 2G plus Z. When total head at A is more than total head at B, when total head at A more than total head at B, the flow is from A to B. When the total head at B is more than total head at A, the flow is from B to A. Okay. The fluid flow direction always from higher total energy to lower total energy. Total head P plus P by W plus V square by 2G plus Z at A, if it is more than the total head at B, the flow is from A to B. That's what. The total energy head is sum of pressure head and velocity head. So, for example, the cross section pipe is uniform. For example, it has given uniform cross section. Uniform cross section is, that means he is giving hint here. What is uniform cross section? Uniform cross section means the velocity, it is having the same diameter. The diameter is same. In other words, the velocity is same. So that means the velocity is not having any importance here. For uniform cross section conduit, the velocity is same. So when the velocity is same, you can cancel both at A and B. Velocity at A is equal to velocity at B. We can cancel velocity A and velocity B. Both are same. So it depends on P by W plus Z at A is equal to P by W plus Z at B. So what is P by W plus Z? P by W plus Z is called piezometric head. So then the energy head depends on the sum of pressure head and velocity head, because the velocity is same. So then instead of total head, you can take a piezometric head because the velocities are same. So when you take a piezometric head at point 1 and piezometric head at point 2, when piezometric head at point 1 is more than piezometric head at point 2, the flow is from 1 to 2. That is the answer here. So he has given all these things here, from higher to lower piezometric head. This is the question which is very, very important and which requires some understanding and some intelligence. So 16, the answer is D. That means the flow is from higher to lower piezometric head as the velocity is same. So this uniform cross section that has given a lot of weightage, you need to understand that. The total head you need to understand, and piezometric head you need to know, and the total energy. And the answer for 16 is D. 2 marks question. Another intelligent question here. If you start answering the questions and if you write the equations, etc., it will take a lot of time. We need to use our intelligence and sharpness and try to evaluate the answer within a short time accurately. So he has given the roughness K by D. Old pipeline has more roughness. K by D is equal to 0.005 and operates at so and so, which is sufficiently high for flow to be beyond viscous influence, and the corresponding F is equal to 0.03. He has given F is 0.03 and he has asked to power increase required. So for F we have some power. Now when the power is increased, if F increased to 0.0375, power increase required, power increase in percentage. So then what is the friction increase here? Let's find out. Percentage friction increase. So find out the increase in friction factor. So one side it is 0.0375, other side 0.03. So increase in friction. So F2 minus F1 by F1. So F1 is 0.03, F2 is 0.0375, improvement factor. So 0.0375 F2 and this is F1, is F2 minus F1 by F1. Increase in friction factor is 0.25, 25%. So then what is the increase in power required he has asked. So power is P is equal to WQHF. So Q is constant. As Q is constant, this is constant, and P is power is proportional to HF. So HF is proportional to friction factor. So the intelligent way of coming to our answer. So he has asked to increase in power requirement, but this power is proportional to HF as these two are constant, and HF is proportional to F here, HF is proportional to F here. Indirectly the power is proportional to friction factor. So the increase in power required may maintain the same flow rate is 25%. So as power is also proportional to this increase, so this is answer is 25%. Intelligent question and need to answer properly with knowledge. So the friction factor increase is 25% and the power is proportional to friction factor. So this is obviously the same value here. The other question. A 15 centimeters diameter pipe is joined to a 30 centimeters diameter pipe by reducing planes. The pressure, sudden cross-section area difference. For water flowing at a rate of 0.115 meter cube per second, the head loss when water flows from smaller to the larger diameter pipe is. Simple problem here. So he has given diameters here D1 and it is enlarged here. What is the equation for head loss due to sudden enlargement? It is V1 minus V2 square by 2Z. V1 minus V2 whole square by 2Z. Simple equation. If you remember the head loss due to sudden enlargement, you can solve the problem. 2 marks. So he has given the data. Diameter D1 is 30 centimeters, which is equal to 0.3 meters. D2, and D1 is 15 centimeters, 0.15 meter. So D1 here, 15 centimeters, and D2 here. And find out V1 and V2. Find out V1 and V2. So Q is equal to A1, V1 is equal to A2, V2. So we have V2 is equal to Q by A1. So Q is 0.115 and A2 here. V2 is A2, pi by 4 0.3 square. You can find out V2 and V1. And head loss due to sudden enlargement, is V1 minus V2 square. So V1 is 6.508 and V2 is 1.627 by 2Z. So this is equal to 1.214 meters. Simple equation. So due to aging, these are all intelligent way of asking questions. So try to understand the theory properly and use theory effectively for answering the questions. Due to aging of a pipeline, its carrying capacity has decreased by 25%. So you have a good number of questions of gate from this chapter, because this pipe flow chapter, which requires the basis of the fluid dynamics, fluid kinetics, etc. Due to aging of the pipeline, its carrying capacity has decreased by 25%. The corresponding increase in the Darcy-Weisbach factor is. So decrease in discharge is 25%. The HF is equal to FLV square by 2GD. Head loss due to friction. Darcy-Weisbach equation is F here. HF, head loss due to friction. FLV square by 2GD. So V square means Q square by V is equal to Q by A. That means Q square. In other words, HF is proportional to Q square. And HF is proportional to K into Q square. And take friction factor out of that. Take friction factor. HF is Q square. And what is F? F is inversely proportional to 1 by Q square. F is equal to FLV square by 2GD. Suppose if you take F here and the Q will be HF by Q square. So F is inversely proportional to 1 by Q square, and take differentiation dF by F, and again differentiation here. Q minus 2, so minus 2 into dq by q. So what is dq by q? And the carrying capacity has decreased by 25%, so dq by q, and change in discharge by discharge as it proportional. So this is 25%, so minus 2 into 25 here, and it is 50%. So the friction factor is 50%. So decrease in discharge is 25%, loss of head, which is proportional to q square, and which is also equal to constant q square. So this constant covers the quotient of friction also. If you take F here, this is inversely proportional here, and take differentiation, and this change has given 25%, so the answer is 50%. So this is another question here. A farmer uses a long horizontal pipeline to transfer water with a 1 HP pump, and the discharge is Q liters per minute. If you use a 5 HP pump in the same pipeline, assuming the friction factor is unchanged, friction factor is not constant, discharge is approximately. So it has increased the power from 1 to 5 HP without changing the friction factor. What happens to discharge? That's what. So we have the equation here. The power is gamma QHF, and you can take HF in the Darcy's head loss. So FI V square by 2GT, the equation, you convert V in terms of cube and D. So the equation is 8FL Q square by pi square GD5. And this P is also equal to QHF. This P is also equal to QHF. And HF is proportional. If you see here, HF is proportional to Q square. Q square, in other words, this is a Q. And to HF, the power, so this is constant here. Power is proportional to QHF here. And this is the HF here, and HF is proportional to Q square, and you can write indirectly P is proportional to QQ. So then P1 by P2 is Q1 by Q2, Q1 cube by Q2 cube, and given P1 by P2 is 1 by 5. So it has given P1 by P2. So this is 1 here, this is 5 here, 1 by 5. So P1 by P2 is 1 by 5, and Q1 by Q1 cube by Q2 cube, and if you simplify, Q2 is equal to Q into 5 to the power 1 by 3, which is cube root 5 by 5 cube. So the equation here, if you see here, this is cube root here. Class I just. So this is Q here, and Q is equal to 5 here, 5 Q, I mean this is the answer here, the answer is D. So see here, this is 3 cube root 5 into Q. And 7. So head loss coefficient in a sudden expansion shown in figure below is. They ask you to find out head loss coefficient. Here you have the velocity here, you have the dimensions here, velocity here, he has given diameter here, and he has asked to find out the head loss coefficient in sudden expansion. So head loss due to sudden expansion is V1 minus V2 whole square by 2Z, and Q is equal to A1, V1 is equal to A2, V2, and you can get the relation between and V1 and V2. So now you can take outside, so this is V1 minus V2 whole square by 2Z, and you can remove, you can take out this V1 square by 2Z. So V1 square by 2Z is 1 minus V2 by V1 whole square. So V1 square by 2Z, so V2 by V1, you know here, V2 by V1. So V2 by V1 is D square by D square, D square by D square. So in other words, HR is proportional to 1 minus D square by D square to the power of square. So the answer is B. Simple here, he has taken discharge equation, and also the loss, you need to find out the expansion loss, I mean the head loss due to expansion, V1 minus V2 square by 2Z, and simple substitution in getting this value. So a fire protection system is supplied from a water tower with a bent pipe as shown in the figure. The pipe friction F is. I am also taking some interesting and important questions which are given in the gate. These are all given in gate examination. You need to have exposure of this. And because we are almost coming in, we have 2 more classes. One class for, the gnosis and R5, one class for boundary layer, and we'll complete this chapter today itself. And important interesting questions here. And we have a Bernoulli equation, you can apply Bernoulli equation between points 1 and 2. So P1 by W plus Z1 plus V1 square by 2Z is equal to P2 by W plus Z2 plus V2 square by 2Z, and loss here. And here we have atmospheric pressure head, here we have atmospheric pressure head, and velocity also 0 because it is the pressure head is constant here, the velocity is also 0. So the velocity is 0 and pressure is also 0. And pressure here is the atmospheric pressure, here we have atmospheric pressure, but we are negating atmospheric pressure right now, 0. And as the water is coming out, here the pressure is also atmosphere, this is also negative here, the pressure is also 0. And the water comes out with the velocity V2 here, the water comes out with the velocity V2 here, V2 is not known, that's why I have taken V2 here. And this is also 0 there, because this is a constant, this is such a big tank, whatever the flow which is coming out, which is not affecting the constant head. So as a constant head tank, we can also take a velocity is equal to 0. So the velocity V1 is also 0. So now the Z1 is 25 meters here. If you take a datum here, Z1 is 25, and if you take a datum here, and Z2 is 0. So if you take a datum here, the point 2 is here, and point 1 is here, and take datum here, Z2 is 0, and Z1 is 25. So 0 plus 0, 25, 0 plus 0, V square by 2G plus HL. So you are getting HL, FLV square 2ZD, HL is FLV square 2ZD, and V square by 2Z, which is equal to 25. So now you have all the values here, 25, F is 0.03, L is the length of the pipe. Bend loss can be neglected. Length of the pipe is 25 plus 150. The students are taking 150. 150 is not correct because we have a length of the pipe 25 plus 150, 175. And the velocity is not known here by 2Z D1. Diameter of the pipe is same throughout. So D is you can take 0.1 plus V2 square by 2Z. So you have a V2 here and everything is known. So V2 value is 3.028. You can find out Q here, which is A to V2. And point 0.024 meter cube per second, so 25 liters per second. So it has given velocity in the reservoir at section A is assumed to be 0, and both section 1 and 2 are subject to atmospheric pressure. You can neglect that. So this is the answer. This is a good question. So it has given the data effort flow of oil, mass density 800 kg per meter cube, and dynamic viscosity 0.8 something like that. And inclined pipe, this is the inclined pipe, and diameter shown, and the pressures he has given 435 and 200. Asked me to find out the discharge of the pipe is equivalent to. So this is also a good question, and he has given the data: mass density 800, dynamic viscosity he has given, diameter of the pipe he has given, pressure at section 1 given, pressure at section 2 is given. So Bernoulli's equation between section 1 and 2. So you can take P1 by W plus Z1, V1 square by 2G, PT by W plus Z2, V2 square by 2G, and losses here. And P1 he has given 435 kilonewton, so 435 into 10 power 3 in Newton per meter square. And mass density is 800 into 9.81 rho G. And the velocity V1 is equal to V2. We can cancel V1 and V2 here, and V square by 2Z. So this is Z1 is 0, and this is we can take same velocity here, V square by 2Z, and which is equal to P2 here. P2 value is 200, 210.3 by 809.81, and Z2. The intelligent way of taking this one is Z1. So you can also cancel the V square by 2Z and V square by 2Z here, as velocities are same. And how will you take this Z1 and Z2? That is an intelligent question. So here Z1 is 0, at this level Z1 is 0 here, and Z2. So the angle is there, 45 is there, you can take a vertical distance. And Z2 from this here, this is from here to here, this is Z2. So the angle is 5 sin 5. So this is the inclined distance. You need to have a vertical distance here, you need to have vertical distance. And Z1 is 0 at this location, this is Z1 here, and this is Z2 here. The vertical here is opposite side, so 5 sin 45. So if it's here, this is 5 sin 45. So you can, you can easily know each and everything, but you may be confusing here. You can take, he has not given Z2 directly, he has given the inclined distance and the angle. You can take the vertical distance with the help of sine. And this V and V are 0, and we have a HL here. And this is the equation here. So HL value, all the values are known, and HL is 26.408. You can take HL is equal to 120. This is a eigen-Poisson equation. So we have 128 mu L cube by pi rho G D4. All the values are known. You can find out discharge here. And mu value is known 0.8 here. And L value is known. L is 5 meters here. And L is 5 meters here. So this L. So this L is 5 meters. This is the L is 5 meters here. And Q is not known here. And this is rho is 800, G 9.81, and diameter is known here. And 0.1, so the Q is equal to 0.12 meter cube per second. Important problem. But the same problem in the flow is reverse. And what happens, how will you find out pressure at section 2? You have the loss of air earlier find out, obtained. So this is PT by W plus Z2 plus V2 square by 2Z, and same pressure equation you can apply here. You can apply here. Sir, class అయిపోతాను సార్ ఒక 10 minutes లో చేస్తాను. So here this is P1 P2 by W plus 5 sin 45. Z2 we have given 5 sin 45. Velocities can be 0 and Z1 is 0 here and HL is here. HL we have the value. Earlier HL we have obtained. HL is equal to 26.408. That I have taken here. So HL is 26.508 and this value we have all the values are known except P2 and PT is equal to 614.5 kPa. So water flows through a 100 mm diameter pipe with a velocity of 0.015. If the kinematic viscosity is given, what is the value of friction factor? Very simple problem. So he has given velocity of the water 0.015, kinematic viscosity is 1.13 10 to the power minus 6. He has also to find out Reynolds number. Reynolds number Vd by nu, the velocity is known here. And the kinematic viscosity is 1.13, so velocity is 0.015 and the diameter is 0.1. So I can find out Reynolds number as it is more than, less than 2000. So I can use the friction factor which is 64 by Rn. So 64 by Rn and you can find out the value of F. Simple problem, find out Reynolds number and use the relation as it is a laminar flow, F is equal to 64 by Rn. So this is, So a 2 km long pipe of 0.2 meters diameter connects to two reservoirs. The difference between water levels in the reservoirs is 8 meters and RT viscosity factor of the pipe is 0.04. According for friction, entry and exit losses, the velocity in the pipe. So anyway, we have 5 more important problems, 16, 17, 18, 3 and 4. So 4 important problems are there. So it takes 15 to 20 minutes. And anyway, tomorrow's chapter is simple, but these questions are important. I will take some more time for explanation. So again, these 4 problems are important. We'll discuss tomorrow early at 10:30, and then we'll go to the chapter notches and R5s. So thank you very much, and we have a short break because of the power failure. I am sorry for that. For the student friends and also for the organizers, and thank you very much for your nice hearing. And tomorrow we'll be taking a small 4 problems in the chapter nation that we'll also take the notches and R5s. That's a very easy chapter and we have some questions and we can complete that tomorrow, and day after tomorrow we'll have a final chapter and lift and drag. So thank you very much student friends. Tomorrow I will meet you at 10:30. Thank you.